And so I'm going to speak about spectral geometry and define the spectral action, but I'd like to give some motivation and then of course the unavoidable definitions and quite technical things. And in the second talk also I will give more precisely an example of the Young-Mills field and how to compute the spectral action. So, as a physicist, my motivation, of course, to study all of this equipment, which is quite involved, comes from the notion of spectrum. So we all know that the notion of spectrum is quite essential, especially in classical mechanics, where you have this Fourier transform. And this means that you are working with Z as a group. In quantum mechanics also we are used to use with self-adjoint operators. Okay, so this means that in analysis we know that this spectral decomposition, so the spectrum or self-adjoint element, is quite important. But it's also important to see that in geometry you also have this application of notion of spectrum. Namely, for instance, if you start in relativity, suppose you have a field, let's call it psi of x, x is in R4, okay, and you ask yourself what's the physical meaning of the coordinates or x mu or the equation of fields. Then of course you have to assume something like the covariance of the field equation. So if you have a metric or say a tetrad field, E mu, which is a solution of your field equation, then okay, you have a solution, but now you pick a diffeomorphism or your manifold, and then you get another solution via this equation, another solution than the first one. So you have plenty of solution. So for me, you arrived at this rough conclusion, which is when relativity became general, then the point disappeared, because this point is equivalent to that point via some active diffeomorphism. So you see, in some sense, the point disappears. So at this level, when you have a manifold, we know that the knowledge of the eigenvalues of the Laplacian is quite important, because this gives you some information about the manifold itself. So you could ask the question, can one hear the shape of a manifold? It was a famous question addressed by Mark Katz about can one hear the shape of a drum? And he answered negatively to this question, but nevertheless I will insist on this question. So in some sense you have two types of approach on the geometry. The first one is based on points, say on manifolds, so you have a point and a neighbors and a chart, atlas, and so on and so forth, and which is the usual geometrical approach. But you have also this approach which is given by the algebra. The algebra is just the smooth function on your manifold. So you have a pointwise product, so you have an algebra. And this is of course the spectral approach. So for me, there is no way in some sense to escape from that. Both quantum world and also relativity drive you directly to this spectral approach. Okay, of course it does not kill this one, but that one is much more important. So this means that in non-commutative geometry, mainly pioneered by Alain Cohn, you start with a triplet, this triplet AHD. And what is this triplet? Well, A is just a star algebra which generalizes the smooth function on your space-time, namely the set of observables. Okay? H will generalize the Hilbert space of spinors, which are quite usual in physics, and D will be some self-adjoint operator on H, which generalize the famous D/ operator, namely gamma mu d mu. okay, some coordinate system. But of course we also know that this is not sufficient, because in physics you also have to take care about renormalization. So here you need something like some energy scale, okay, so I call it lambda. And you also know that you have to handle with some actions, okay, when you have your field. So there are plenty of actions. The most famous is Einstein-Hilbert action, which appear in gravity, and also these Young-Mills and Higgs action, which appear when you are when you work in particle physics. So here, all these actions will be replaced by the so-called spectral action, which is defined by something which depends on d, on your scale parameter here, and a function f. We'll see that this f is not essential, but it is even if it's a simple definition, which is just the trace of f of d over lambda. So you have your renormalization here. F is an extra parameter. You just take the trace of this. Well, of course, since d is an unbounded operator, well, you have to be sure that this makes sense, but that's the whole story, actually. So you see, the motivation for doing non-commutative geometry is, first of all, that you have all classical geometry in your pocket. That's for sure. This means that you have also in your pocket all unsolved problems which appear in usual geometry. But since we are physicists, well, okay, no fear. So the question is, can one hear the shape of a universe? Okay, and we already know that for a shape of a drum, the answer is negative. But I do insist. I want to hear the shape of the universe. Okay, that's really the point, because here the dogma is everything should be spectral. Okay, so the only thing you have in your hand is the spectrum, the knowledge of the spectrum of something. So this means that your geometry should be based on the notion of algebra, which means the spectral approach that I described before. But here you gain something, and this is important because you can describe a world where eventually there is no points. Okay? So you could, of course, say, well, I can work with matrices. Well, it's usually in physics when you have gauge theory, so you have matrices, so you have no really points, but you have vector set. But more essential than that, because you have a lot of algebra, non-commutative algebra, we have no real points beyond. But more important is the fact that in this framework, what you have is that you put at the same level discrete sets, the description of discrete sets and continuous sets. That's really essential because, well, mathematically there is a wall between the two sets. You know, discrete set and continuous sets are definitely not the same objects. But here you can really work with these two pieces exactly at the same level using this algebra. So now we enter more precisely after this motivation in the definition, a real definition. So a spectral triple, okay, is based on this triplet, where A is an involutive unital algebra with a faithful representation pi on some Hilbert space. All my Hilbert space will be separable. And the second object is that you have a self-adjoint operator, which is unbounded a priori, with a compact resolvent. The essential consequence of this is that it will have a discrete spectrum. And you assume only that the commutator of element in the algebra with D is bounded. That's it. Okay, so if D is a differential operator and A is a function, then it's just the multiplication by the derivative of the function, right? And when A has no unit, which corresponds to the case when M is not compact, manifold is not compact, then you assume that the resolvent times an element in the algebra is compact. Okay? This is a nice replacement. So just, well, also you could say, well, I have A and D, that's sufficient. Since you have only one separable infinite dimensional Hilbert space, you could say H is just a gadget here, but it's not at all a gadget, because you know it's a receptacle of the representation of A, and also on which D acts. And via representation theory, you know that there are a lot of inequivalent, or even not quasi-equivalent, faithful representation for the same algebra. So this is where H play a role. So you have to be aware of that. When you have a spectral triple, well, it is said to be even if you have a grading. So grading operator is just gamma 5, okay, which is a self-adjoint operator which commute with the algebra and anti-commute with D. So this means that D is an odd operator with respect to this chirality. And this triple is said to be real if it has a KO dimension D, which is an integer modulo 8. And the definition is that if there is some antilinear isometry J, which has this relation with previous objects, and where all coefficients epsilon, epsilon prime, epsilon, epsilon is a table of signs. So why do we have this? Because you want to mimic the spin situation, so you have to pay attention to the Clifford algebra representation, and we'll know that there is this famous spin chessboard 8x8, and this is precisely to replace this situation. Okay? So nothing else. And this J is actually quite important in mathematics, because it also an origin in C-star approach in algebra, because it comes from the Tomita-Takizaki theory. This means that you also have to admit that if you define this representation of an element in the algebra, which is denoted by this, I put a star here because J is antilinear. Okay, so this is just a representation, and you have to admit that this is the role of J, but this representation commutes with the original one, and also commute with the commutator with the algebra. Okay, so thus all these axioms are just algebraic, but of course you have to enter a bit in the analysis, and you will say that your spectral triple is D-summable, D is a number, if the singular value of that operator, which is bounded, is under control, like that. Okay? So this means you have in your mind the notion of dimension. And then you have to assume also something which is due to the smoothness, because you see, when you have no points, how to define smooth function on your set. So you have to assume that the algebra and the commutator with D are in the domain of D and this power of delta. What is delta? Is just the commutator, or is the absolute value of D. So it's the first appearance of the absolute value of D. Why? Because you know what, if D is a Dirac operator, so it's matrix valued, while its absolute value is only a scalar operator. So it's better to work with D or absolute value of D or D squared, because it's simpler. And then you have two other axioms. I don't want to enter into the details. But the idea essentially is that when you have, excuse me, when you have the Laplacian, you have all this scale of Sobolev spaces, to define how your Laplacian is defined, just to be sure, because it's an unbounded operator, but everything goes well. So this axiom is just to define this Sobolev scale. And you have another condition, let's call it the orientation condition, which tell you that the chirality, so gamma 5 if you prefer, is given essentially by some Hochschild cycle. So I will be a bit lazy about that, but I would like to emphasize something which is really essential, namely the fact that you can, with this arbitrary algebraic setup, to reconstruct everything. Namely, this is a theorem given by Alain Cohn 4 years ago, and actually it took him, I guess, 12 years before to get a proof after his conjecture. So I don't think it's a trivial result at all. What's the result? When you have a spectral triple, and the only thing you know is that the original algebra is commutative. Okay, so you could think as a set of functions acting on your manifold, but you don't know that you have a manifold which satisfies all above conditions, on which I was lazy. Then there exists a compact speed C manifold M such that A is precisely the smooth function on M and D is a Dirac operator. Okay, so how to do that? First, as a set, M is just the spectrum of the closure, the C-star closure of A, so you have an algebra, so this makes sense. D, you prove that it's, in this context, it's a differential operator, but it's known only by its principal symbol, so it's not unique. Okay, so we have plenty of them. And the J, what we saw before, encodes the nuance, there's a little subtle nuance between spin and spin C structures. And the spectral action, the trace of F of D or D of lambda, selects, if you make some, let's say, minimization process, like in every action, select for you the Levi-Civita connection to the, so it selects the Dirac operator D slash. Okay? So D recaptures the original Riemannian metric on M via some distance, the so-called Cohn distance, on the state space of this C-star algebra of continuous function on M. Okay? So what's the conclusion? The conclusion is yes, indeed, we can hear the shape of a spectral triple. Okay? If I gave you a commutative spectral triple, I can give you the manifold, the Dirac operator, everything on it. So the knowledge of the spectrum of D, this is what I mean, that one can hear the shape of your triple or your universe, if you admit that the universe is described by something which is algebraic. And so the knowledge of the spectrum of D and also the volume form via its cohomological content is sufficient to recapture everything, namely the metric and the spin structure. So the role of D is to provide you a metric, and also, since you have, when you have 1D, you can add a connection, so you have another candidate. So its homotopy class represents the K-homology fundamental class of non-commutative space. So you see here, you work with non-commutative space, and you have plenty of them. Okay, not only manifolds. That's the idea. So just to remind you that one cannot hear the shape of a drum, not only because there is a boundary, but essentially because the spectrum of the Laplacian does not determine fully the metric of M, and even if its conformal class is given. So, as example of spectral triple, you have, of course, all, I do insist, all classical geometry, with all, of course, difficulties. But you also have particle physics. Why? Because you can put, as I said, matrices and SU1, SU2, SU3, and so on, and so n if you want, in some quantum unification scheme without problem. It also appears in solid-state physics with first it was with a quantable effect, a control which has some origin precisely in K-theory based on C-star algebra on quasi-periodic system, but today there is an industry on that. Of course, on cosmology, I suppose that we'll hear something today about that. But not only this, since you are in a non-commutative world, you can have all these quantum deformation like, Moyal deformation, Berezin-Toeplitz deformation, and all deformation that you can imagine. Also, something which is not a quantum deformation necessarily, which are all the quantum groups, okay, and there is also some industry about that. But also in dynamical system, especially the C-star dynamical systems, and of course you have all different applications that I will not describe. Okay, so that's something, and now I'd like to speak about something which is totally different. Okay, I would like to speak first of all to address the following question. Sorry, when you know the boundary operator on some Hilbert space, you know what is a trace, and the question is a trace always proportional to the usual trace? Of course, on the set where it is finite. Okay, that's a natural question. And Dixmier answered in 1966, the answer is no. And that's very strange because, well, a trace is just a sum of, the eigenvalues, it's kind of unique. Well, the idea is the following. I define for T a compact operator, so it has a discrete spectrum. Mu n of T is just the nth singular value of T, arranged in the decreasing order. And now you sum the first eigenvalue and you renormalize by the log of the number of terms, and take the limit when n goes to infinity. Okay? Why not? And you could see this as a Dixmier trace. Actually, well, this is not really a definition, but this is sufficient to understand what is going on. Namely, the difficulty here, is that, well, why should this limit to be additive? Namely, if T is T plus T1, T1 plus T2, why it should be the sum of T1 and T2? Because you have this renormalization, okay? But actually this is a paper by Dixmier, so he proved that this, well, not exactly that one, but anyway, this is additive. So since it's based on a singular value, and singular value is invariant by a transformation, unitary transformation, you see, then automatically it is a trace. So important things is that the Dixmier trace of a trace class operator is always zero. Why? Because, well, this sequence here with respect to capital N converge if your operator is trace class. So since you divide by the log of n which goes to infinity, of course the limit is zero. So this means, this is a trace, but it's always zero on the trace class operator. This means that these mixed traces are not normal, namely they don't commute with the supremum. Okay, they are singular. And likely, like you have a singular measure, you have singular traces. And the motivation for that, the use of that, is the following. We all know that the series 1 over n diverges. But this is just, you could say, a technical point, but it's not a technical point, because in physics, both the electromagnetic or Newton potential are in 1 over r. Okay, so you have the same singularity in one dimension. So this means that since you can generalize this in any dimension, this means that everywhere in physics you have this appearance of the Riemann zeta function, which is a map from the complex number to this sum. Okay, So this means that in renormalization you always have this zeta function everywhere. So this means that this Dixmier trace is around. Okay, that's the message. And more than that, essentially in noncommutative geometry you have this notion of infinitesimal. We all know what is an infinitesimal in classical geometry. You have infinitesimal for the 1, for the 2, for the 3, and so on. But here this is replaced by compact operators. Why? Because for many reasons, especially because of K-theory and so on and so forth, compact operators weight nothing. Okay, but nothing means which is some infinitesimal, and precisely the Dixmier trace controls the logarithmic divergency of the trace. Okay, this is precisely this logarithmic divergence which appear here. And why this is important, because you see this means that you can define infinitesimal of arbitrary order, not only of integer order. You are precisely in the right setting for doing that. So now what I claim is that this has a relation which was purely algebraic, but this has a relation with something which comes from pure geometry. Namely, you start with M, a d-dimensional compact Riemannian manifold. I assume that there is no boundary, and this manifold is endowed with a vector bundle. Okay, so you have M and a vector bundle E. You choose D, a pseudo-differential operator which is elliptic and for the 1. Okay, first step. Second step, you choose P, again a pseudo-differential operator of integer order. Then Wodzicki, 30 years ago, introduced the following eponym residue, namely you consider the trace of P times the absolute value of D to the power minus S. S is a complex number a priori. This could be trace class operator, so no problem if S is large enough. You take the holomorphic extension and you take the residue. Okay? Okay, that's complicated, but that's life. But what you see here, there is no D here on the left-hand side. And what I claim that this makes sense because precisely this is a result of Wodzicki. This map, which is essentially a zeta, the equivalent of zeta, Riemann zeta function, has at most simple poles on Z. And second, that these strange objects actually is totally computable. It's equal to the integral on your manifold of some density here, and this density is written here is just the integral of the symbol of P at the order minus the dimension. D is the dimension of the manifold. Okay, integrate on the cos-sphere bundle. Anyway, that's the result, and as you can see, there is no D here, right? So this makes sense. This doesn't depend on D. So D is a kind of background here, and now that's enough to understand the second point, namely that this is a trace also, because you see everything is as S equal to 0. So if S equal to 0, D disappears. So if you replace P by P1, P2, so you have trace of P1, P2, so you just commute, it's a trace. So this means that this is a trace on the algebra of pseudo-differential operator with integer order. And, well, it's a result of Wodzicki, it's a unique trace up to dilation. But what does that mean? It means that this has been generalized by Alain Cohn in 1988, namely, if you have a compact Riemannian manifold, d-dimensional, and a vector bundle on it, and assume that you have pseudo-differential operator of the order precisely minus dimension, you see dimension is critical point. Then the Dixmier trace coincides with this purely geometrical object. Why? Because both are traces and you have uniqueness. Okay? So, you see, this was defined for purely algebraic reasons. This is purely geometrical and they are related. Okay, so now I would like to enter a bit in the techniques because we will need it later on. So, when you have a spectral triple, since you want to mimic also, you know, what I said before, namely the kind of smoothness you can define and what are the sub-F scales and so on, what are the pseudo-differential operator, since you have only an algebra, an Hilbert space and D. So you define this map between bounded operators and you put this representation associated to absolute value of D, and you will declare that T is an operator of order less or equal to 0 if this map is smooth enough. Okay? And when you add that, you define the operator of order less or equal to alpha, any real number, if this product is in op 0. So this is a consequence of the first definition. So, as which has been made for that actually, the product of operator of order alpha and beta is of course in the operator of alpha plus beta. And if you want to see how it works, well, since you have in mind in your hand only A and D, so operators are always this form. An element is the algebra, absolute value of D, or commutators with an element is the algebra with D, and some power of D. So A is of order 0, D of order 1, B is of order 0, D of order 1, so the commutator is of order 0, and D minus 3 is of order minus 3. So 0 plus 1 plus 0 minus 3 is op minus 2. That's simple as that. So now we are ready for a definition of a pseudo-differential operator, namely they are always of the form absolute value of D to the power minus something times something. This something should be in the algebra generated by A naught, this opposite algebra, D and absolute value of D, plus something. And this plus something is as usual when you work with pseudo-differential operator, because you work modulo something, modulo smoothing operator, and here you want to mimic this up to this smoothing operator. Okay? So this is the idea. So essentially it has this form plus something which is quite regular. And in particular in the commutative case, when your algebra A is C infinity on a manifold, then these pseudo-differential operators are precisely the usual pseudo-differential operator on your vector bundle. So I insist you have mimicked the commutative situation. So when you have a spectral triple, you know what is a pseudo-differential operator, and you have this map, what we saw before, which is a zeta map, and this makes sense. This is a real number if S is large enough. S is a complex number, and this means that this operator here is trace class in this case. But at some point S, you have an explosion. Okay, so the dimension spectrum of your spectral triple is the set of all the points in the complex plane where you have problems, and the problems are always created by the poles of this map. Okay, so for a manifold you have a notion of dimension. Here the notion of dimension is replaced by dimension spectrum, which is a set of points in the complex plane. Okay, and it will be said to be simple if all poles are of order at most 1. And then now you are ready to define a non-commutative integral of a pseudo-differential operator, okay, P. It is defined as before by Wodzicki, but here it's a generalization by this formula, okay. Just technical point, since the beginning I always assume that the absolute value of D is invertible. Well, it's not the case. You have just replaced D by D plus P, where P is a projection on its kernel. This kernel is always finite dimensional in this situation, so you know, it's a rank 1 operator, so no problem for the remainder. Okay, so when you have 1D, when you have a Dirac operator, of course you have fluctuation of this operator, namely you can add a connection. So what about connection here? So you need to have a notion of 1 forms, and these 1 forms are just, as it should be, of the form ADB, A and B in the algebra, and DB is just a commutator with the Dirac operator, or with D, which is Dirac-like operator, you know. And precisely in the commutative geometry, the 1 form associated to Dirac operator are precisely C of dA, so the differential, usual differential of A is a smooth function, and C is just the Clifford multiplication. You know, you have the gamma matrices in the game. And here there is a little subtlety, because when G exists, it does not always exist, when it exists, since you want some commutation relation between D and D sub A, where you add to D this correction, which is a 1 form, then you have to replace A by A tilde, which is a symmetrization with respect to J. Well, it's a bit technical, but it's important precisely in this situation. So, you see, when you have 1D, you can make this fluctuation, so you can add connections, and of course you have other spectral triples associated to these new operators, or this new one, which is the same, but you have this symmetrization about your connection. So, you can prove that a fluctuation of a fluctuation is a fluctuation, but more important is the fact that the unitary group of the algebra is gauge compatible with this adjoint representation, namely everything makes sense, and by this I do mean that if you have a self-adjoint 1 form and a unitary element in your algebra, and you define this strange unitary operator on H, then this operator is actually equal to that, and here you can recognize usual gauge transformation. Okay, so everything goes well. That's the message. And of course, the important point is that here you work with the unitary group of the algebra, and not every group, especially Lie group, is a unitary group of an algebra. This means that you have a selection process at this level. And also remark that the inner fluctuation is not a symmetric relation, namely you can have a zero fluctuate Dirac operator while the original Dirac is not zero. So that's rather strange, but it exists. Okay, so just to remind you that this is the definition of the zeta function associated today, and there is a result proved by Shamseddin and Cohn, and extended by myself and Cyril Levy, which is in Potsdam now. But if you assume that you have a spectral triple which is sympathetic enough, okay, of dimension D, then for any 1 form, self-adjoint 1 form, then the difference between the evaluation of the zeta function for the bare D and the fluctuate D is given by a finite sum of non-commutative integral. Okay? And this non-commutative integral that you can have here, if you look at it, it's something which is usual in quantum field theory. Namely, you can define a tadpole of a certain order. D is a dimension, so D minus something, some integer, as this strange definition. Okay? But if you look at an example where L is equal to D, so this term is 0, so you add this and this, so you end up with this integral, which is simple, and you can recognize something here, which is a fermionic loop here associated to D minus 1, and some leg here, which is associated to the fluctuation A. And this means that you can compute this exactly what when you compute Feynman diagrams, you can, this is replaced, you know, by this strange computation. And we all know that there are divergences, but you see this strange notation of integral bar, quantum integral, is precisely here to take care of all these divergences. So, in commutative geometry, where you start with a smooth function on a manifold, the Hilbert space is a square integrable spinors, and D is D slash. Then what is the non-commutative integral of a pseudo-differential operator? Then actually this is the coefficient in log of t is the asymptotic of the heat trace. You know, here you have the heat operators associated to D, and you put P in front, and you look at what happens when t goes to 0. Okay? And this coefficient is independent of D slash, which is previous remark. And if you compute this, and you can prove in this case that this has an asymptotic behavior when t goes to 0, which has this form. Okay, so you have coefficient, and t to the power k, k is a summation index. Here you have the order of your operator, d is dimension, plus something which has a coefficient in log t. And when t is equal to 0, when k is equal to 0, you see what a prime 0 is the coefficient of the log. And precisely this is the result. Okay? And when a prime here is not 0 for different k different from 0, then this means that you have poles at 0 of this function, of this zeta function, which has some order greater than 1. And this appears unfortunately even in quantum deformation. So that's all it is about. To control, to be able to compute these numbers. So, few words about fluctuations, namely that in commutative situation, then there is this strange behavior, namely that when you make a fluctuation, there is no trace of this fluctuation, so you have this equality. So you are obliged to use only this definition for the fluctuation. And what does that mean? It means that in non-commutative geometry, if you want to work with abelian gauge field, you have to go outside abelian algebras. This means that a commutative manifold could support relativity, but not electromagnetics if you want. Okay, that's the conclusion. So, I guess I will end up first part here. In the commutative case, what is the dimension spectrum of a commutative geometry? Well, it is simple, and the dimension spectrum is just a set of all integers less than d. Okay, so you have infinite number of in this set, point in this set, but they are simple, they are just integral. And we proved with Cyril Lévy that in commutative geometries there is no tadpoles, never in this case. Now I'd like to continue with the second part, which is the search for a good action functional, which is important in physics, how to define an action. So there are plenty of action in physics. We have, for instance, this Einstein-Hilbert action, which is what? Well, you have a manifold with a metric J, and the Einstein-Hilbert action is just the integral of the scalar curvature on your manifold. Here I put a sign minus because I choose the curvature to be positive for the sphere. So in the previous algebraic context, then this can be written like this. It's nothing else than the non-commutative integral of d slash to the power d minus 2. Okay? And what's the interest of this action? Well, if you restrict yourself to the set of whole metrics on a manifold which preserves the volume, okay, this is important. We don't know if the universe has a growing expansion or not, and so there is this famous theorem by Hilbert that if J is in this set is a critical point of this action, if and only if M with J is an Einstein manifold. And Einstein manifold means that the Ricci curvature is proportional to the metric itself. So this means that if you use trace, the scalar curvature is just proportional to the dimension of the manifold. So it's constant. So, but you see, you want more than this because, well, of course, the scalar curvature is invariant by diffeomorphism and so on, but you could take functions of the scalar curvature, and of course, this is also an invariant under the diffeomorphism group, and there are others not of this type. But this means that you have to define what you want, and what we want is something which is additive in some sense, namely that if you have observables which concern disjoint geometries, you want to get something which is just a sum of the two previous parts. So this is the first remark. The second remark is, as I said a little bit before, the spectral triple fits perfectly the quantum field theory. It is said that the inverse of the Dirac operator can be seen as a propagator for your fermions. Here everything is Euclidean. And this means that you can compute, in principle, all Feynman diagrams, okay, with fermionic internal lines. And this also means that when you have D and you have all this fluctuation, what you have in mind is just that the gauge bosons are only derived objects, they are not primary objects, okay? And they are obtained by this internal fluctuation associated to one form. So there is an algebraic setting for that, which is just Morita equivalence, and which is something which has nothing to do with fermions, but or bosons. But this is why you can justify not only to mimic the commutative situation, but to do something like that. So the main idea of Shamseddin and Kohn is that they wanted to get a theory which is pure gravity. Okay, and so the action depends only on what you have in N, so the triple spectrum, spectral triple, so it depends only on the spectrum of D. So the definition of spectral action is precisely this, so the trace of F of D square over lambda square. So I will comment about the square in a moment, but forget it. So here lambda is just plays the role of a parameter, so it's a positive number. F is a positive function. We'll see later what is the role of F. And of course, you have to assume that F of this quotient is trace class operator. Okay? So this depends on F. And if you want to see the algebra in action, you have just to replace D by a decoration of D, namely D sub A. Okay, fluctuation of D. So another definition could be just to use the trace of f of d over lambda, so no square. When here you have to assume that f is positive and even, and the link between the two is of course that you replace a function f of x by f of x squared. So it's a kind of transformation which is up to you. Anyway, I prefer to work with d squared because d squared looks like a scalar operator. Okay, so it's better. So anyway, so when f is this function, okay, characteristic function of this interval, when what is f of d over lambda, you have just to count the eigenvalue of d, which are between your energy scale. Okay, lambda could be seen as some energy, even if it's the wrong dimension. So if you admit that this action as some asymptotic series when the energy is pushed away, then you end up with some effective theory, and you see if you replace d by a decoration with one form, then of course your life is more complicated because the computations are more complicated, but it's exactly the same. So if you add this fermionic term here, here you have the presence of J, then you can say that, you can prove that you have the full action of the really standard model of particle physics. Okay, maybe, I don't know if you will talk about this. Anyway, so another famous action in physics is the Yang-Mills action. So just a few words about it. Well, let me remind you the classical situation where you start with a compact Lie group, J, and you begin with a one form which is valued in the Lie algebra of your group. So this is a connection. So you take the curvature of the connection, okay, and then the Yang-Mills action is nothing else than the famous F mu nu, right? So in this algebraic context you can do exactly the same. I don't want to do it, it's a little bit complicated, but you can also study the critical values for this action for an arbitrary spectral triple of dimension d. This has been done by Alain many years ago, but this is not really in fashion today, even if it's still interesting, I guess. And the reason is that actually the spectral action is much more conceptual than the Yang-Mills action. Why? Well, you know, when I said that I replace d by d plus a, so in some sense you start with d, so this makes that you make a difference between the gravity and the matter, but you can split a into two parts, you see, or you can divide also d in two parts. So this distinction between gravity and matter is totally artificial. So this means why this is more interesting to work with spectral action. So for instance, in any minimally coupled standard model, then you can prove that the Yang-Mills action for vector potential and the Einstein-Hilbert action for the Riemannian matrix are part of the spectral action. Okay, so everything here is contained in the spectral action. So this means that this action has a lot of advantages. The first one is, of course, the simplicity. The formula is quite simple. Okay, so in particular, if f is a cutoff, is characteristic function, then the spectral action is nothing else than the counting function. So you count the eigenvalues, including multiplicities. The second advantage is that the positivity is preserved, namely when f is positive, you get correct sign for the Euclidean action, namely the actions for gravity, Yang-Mills, and Higgs couplings are all positive, and the Higgs mass term has a right sign. So Alan Cohn is pretty proud of this in general, but I think it's for nothing, because actually he has mimicked the Gilkey approach of the heat trace heat kernel techniques, and so everything works like that. So since all physicists always use this, I mean, it's almost cheating. I mean, it's trivial. Another important point is the invariance. Invariance, you know, here the invariance group is much stronger than the usual diffeomorphism group what you have in gravity. Here it is the unitary group of the Hilbert space. So you have to lift everything at the Hilbert space level. Okay? And well, you also have to prove that this lifting is unique in some sense. It is not. This means you have some physics behind. So you have to justify your choice. So that's not obvious at all. Well, of course, life may be a bit complicated, so I have to deserve my salary. So there are some defects. So this action is not local, okay? And while you could say it becomes local when you replace the spectral action by its asymptotic expansion, okay? When lambda, when the energy goes to infinity. And well, of course, you have the difficulty. The difficulty, you have to check that your operator you are dealing with F is actually a trace class, and you are able to do computation. Everything is there. So, what about precisely this asymptotics when the energy goes to infinity? So, assume that you have a spectral triple. Assume that it's a good one, okay, of dimension d. Then the trace of this it operator, you assume, I insist, you assume that it has this behavior. So alpha could be a complex number in the dimension spectrum, and you assume that you have this asymptotics. Then you control the coefficients. The coefficients are precisely given, for instance, when alpha is negative, by the residue as before of this zeta function. Well, gamma is just a gadget here. The gamma function always appears. And for instance, when t is equal to 0, which is quite important because this is where the coefficient is invariant by dilation. So this has really physical significance. Then A0 is just the evaluation of zeta d at the point 0, and here you have these extra things where the kernel of d appear. So if you admit this, then the asymptotic expansion on the positive part of this eventually a complex set of numbers behave like that, namely it's just something which depends to lambda to the capital to the beta, and beta is a positive number here, and we'll see what happened in the commutative case later on. Here, this is a part which depends on d, so this is just non-commutative integral, and f is what? F beta, this coefficient is just a momentum of this function. So you see, you have split every object in three pieces here. When beta equal to 0, then you have this coefficient plus something, and this something involves, of course, the full Taylor expansion of f at 0. And since you know what happened for this coefficient here, and I remind you, we already saw how to control this difference between a bare d and a fluctuate d, okay, before. It's important because this is a constant term, so this is invariant by dilation, okay. So, a few remarks in the commutative case. In the commutative case, then d is just kind of d slash, and so the asymptotics is like that. the first term is capital lambda to the power d, and then to d minus 1, d minus 2, and so on. Here you have some coefficient depending on d or d square, and here coefficient depending on f. But this has been proved, when you look at, this is where proof are important in mathematical physics, this has been proved for smooth functions which are actually even more than that, which are Laplace transform. And of course this is much too restrictive because it doesn't cover even the heat kernel case where the function is like that. Okay? So you can prove that this asymptotics makes sense, but in the Cesaro sense, in the distribution set, K prime, where K of R are the smooth function on which you have a nice behavior, a controlled behavior of all derivative. And you can prove that, of course, the counting function is not smooth, but it is nevertheless in this distributional set. And the previous behavior that you have here is wrong beyond the first term, but is correct in the Cesaro sense, namely you have more terms, but they involve also the Dirac distribution and its derivative. Okay? So you have to be careful when you use this asymptotics, when you use the asymptotic expansion. So here the spectral action is not local, okay? Spectral action is that. Here this is something else. And with something else you can be in trouble because this asymptotic series does not necessarily converge. Okay? Namely, Arthur Zajac has proved that, for instance, in easy case, all even dimensional spheres with d equal to the usual Dirac operator have divergence series here. Okay? And strange enough, all odd spheres have a convergence series, but even more than that, you have only a finite number of terms. So you see, you want to extract physical information from that, but here you have a number, here something which is not really defined. Okay, so you have to be really careful about what you are telling. So now I would like to treat an example, and this example is precisely where your manifold is not compact. Okay, so I would like to treat an example of a Young-Mills field, so quite easy, quite elementary. So it's a joint work with Cyril Levy and Dmitry Vasilovich, who is in São Paulo in Brazil, and we chose this commutative model. So our manifold is just a hyperplane, even dimension, with a trivial spin structure given by this spinor bundle. We use D as a free Dirac operator, and dA the standard Dirac operator with a gauge connection. Okay, and H is, as usual, the square integrable spinors. So if you prefer, in local coordinates, if you always work in locally, so it's gamma mu d mu, and D sub A is just, you add A mu. Okay, and A mu is just section of M with values in the homomorphism of S, namely some representation of your favorite gauge group. Okay, so, and we want to compute the spectral action for this operator. In general, you have to make some hypothesis, namely about A mu, or about its field strength. Namely, you have to assume that this fall off sufficiently fast. But we will see later that this so-called weak field expansion is not totally necessary. But here we face a problem. Namely, of course, the hyperplane is not compact, so the Dirac operator has a continuous spectrum. Okay, so you have to work. And the first result is to find a good algebra. So we choose the Schwarz function on this hyperplane, same operator, same Dirac operator, and the first thing is to prove that you already already have a spectral triple. You can do that. And then, when you have a spectral triple, it's almost immediate. You can show that when you change the OD, you also have another spectral triple. Okay? But again, we have the same problem, namely f of d square, or d over lambda to the power square, is never a trace class for any f. Why? Because when you think in terms of pseudo differential operator, f of d square depends only on xi. You have two variables, x and xi, depends only on xi. So any integration about on x, on the manifold which is the hyperplane, will diverge. Okay, so it's never the case. So this means that you have to define a good notion of spectral action. So we did this. We made the difference between the bare D and the decorated D, and we take f on each part and takes a difference and takes a trace. So this is a variation of the spectral action. Okay? So we could say why not, but also why. And what is the interest of this variation? Well, first of all, it makes sense for every non-unital spectral triple. Okay? Second, well, the difference between this geometry and this one is actually the same. They are Morita equivalents. So you are working with the same geometry. Okay? Another argument is that the heat asymptotics, when lambda goes to infinity, the coefficient which is invariant by dilation, so there is no dilaton here, is this difference. And remember, we compute already this difference, but only when A has a unit. Here, which is not the case. The Schwarz function, of course, has no unit. Okay. So I remind you that the zeta function is just this definition. So the interest of this is also to avoid what you can see in many physical people, namely the extra smearing function h, just to regularize your trace. So if you add something which is a spatial regularization, then of course you end up with something which is trace class. But h is an extra parameter, and it's difficult to justify the meaning of it. Okay, so you avoid that. And the last argument is that this spectral action is actually, in principle, quite simple to compute, because it's just the integral of f prime, here you have your function f, times something, and this something is a spectral shift function, on which I will say more later. So you have this formula, and this formula makes sense for a large class of function. Okay? But I insist, this is not a definition of a spectral action. This is just a definition of a variation of the spectral action. Okay? So, this spectral action has been studied in the weak field expansion in the following sense. So, as I said, you assume that f is a Laplace transform of something. Why? Because you want to use the heat kernel techniques. So f is a Laplace transform of phi. So you can write again this spectral action. It will be the integral of this function phi times this, and this, if you normalize the coefficient here, is just a trace of the difference between the two heat operators, which is a subtract heat kernel. Okay? And then if you make the asymptotics when lambda goes to infinity, then it goes like that. You have powers of lambda, so 2m is dimension, minus something. This something k goes from 1 to infinity, so you have only one coefficient over 2, times something which depends on phi, which is a momentum of phi, times something which depends, of course, on your operator. And you see, you want to have some information here. Here this is number, if it exists, and here this is a series. And this series, in some sense, is valid only when the field and their derivative are small compared with your energy scale. Okay? This is why it's called the weak field expansion. But, you know, this is where our normalization takes place, because in the spectral action, the terms which depend on all which is quadratic in F, and F is the curvature of A, and all its derivative governs the propagator, namely the ultraviolet behavior of the propagator. Okay? While the remaining of the series, involving something which is in F cube, F fourth, and so on, determines the vertices. Okay, and that's enough to control what's the behavior of your field. And Walter von Zwijlkom proved the following last year. He proved that if first you restrict to the terms which are quadratic in F and all derivative, he restricts to the compact manifold. Here we are in something which is non-compact, so totally different. And he used not the spectral action, but he used its asymptotics expansion, and we saw its difference. And not only that, he used a truncation of it, so he used the first term and forget about the remainder of the series. So if you admit this, then a very simple power counting argument shows that this Yang-Mills model is super normalizable. So this is rather strange, because, you know, we all know that in dimension 4, for instance, so m equal to here, I guess that the fact that the Yang-Mills is renormalizable was awarded by a Nobel Prize. So, you know, it's not trivial argument like that. So this is where you can see, you know, the full power of spectral action, non-commutative in action, geometry in action, because here we want to use a different idea. I mean, we want to compute really the spectral action, not its asymptotics, as a function of the field strength in full generality, and then control its ultraviolet regime. So the method we use is a Russian method initiated by Barvinsky and Vygotsky, and it's called the covariant perturbation theory. And the result is the following, is that the spectral action density behave like 1 over P4 when P goes to infinity. When the momenta goes to infinity, it behaves like that. And of course, this means that the propagators grows at large momenta, so it's not super normalizable at all. Okay? So, how to do that? Okay, so let's say that this is a joint work with J. Levy and Vasilevich. For the large and precise set of functions, I don't know if yeah, I have time. Set of functions, well, the terms which are quadratic in F and all its derivative is precisely this term. Not quite simple. It involves the Fourier transform of F mu nu, here and here, times a function depending on the momenta, and this function has an explicit formula which is written here. It depends on F. The bracket means that it's not the derivative but the integral, first integral, and you have a precise formula, and so you can compute this asymptotics, and this asymptotics is like this. So you have, this is the rank of your spinor bundle. Cf is just the evaluation of F, or more precisely of the integral of F at 0. You are here. Sorry, I'm in dimension 4. So this begins in lambda 4 times the inverse of P to the 4 plus something. And you see, what is important here is that you can see coefficients which appear here. These coefficients CF times lambda 4 are the same as in the lambda 0 term in the weak field asymptotics of the spectral action. So a 0 term, let me try to find it. Wow, it's here. A 0 term here is precisely the main behavior of the spectral action, the first term. So the coefficient is usually called the cosmological term. Okay? So this this coefficient is exactly the same. So that's important because here this coefficient has been cancelled here because we are in the non-compact case, so the volume of your hyperplane is infinite, so I have to subtract the first term. This is what I have done. Okay, but nevertheless it contributes to this cosmological term if you deal with more general spectral triple where you allow metric perturbation. You see, that's interesting remark. So this creates some intimate relation between the linear term in low and high momenta asymptotics of the spectral action. Okay, not trivial remark. So also the spectral action is not local because, well, we use only simple definition, but in some sense it becomes local after your asymptotic expansion. But here this is not what I have done. Okay, here the covariant perturbation method is a way to control all the non-localities globally. Okay. Also a remark is that the spin C structure is not necessary to do that. You can work with any Laplace type operator in a situation. So what about what I said about the formula, namely the Krein spectral shift function? Well, it first appeared in scattering theory, and it's based on the following quite technical point, but remarkable important. So if you start with a couple of self-adjoint operators on some Hilbert space, then the spectral shift function psi of lambda, which is the original definition of Lifshitz. Lifshitz is, Landau Lifshitz, famous physicist. The Lifshitz trace formula. So the trace of f minus f h naught, so h could be seen as a fluctuation of h naught, is like this. It's the integral of f prime times psi of lambda, and this is the definition in some sense of psi. We'll see later on a better definition, but that's the idea. So what is f? If, for instance, if f is this characteristic function, okay, then psi of lambda is a kind of trace of the difference between these two spectral projections associated to these two operators. Okay, so this is a kind of regularized trace. So this psi of lambda is a regularization of the difference of the eigenvalue counting functions. So here you can see that this has been used in many different situations. Psi of lambda minus, is also the freedom index of this pair of projections, and it also the spectral flow of H compared with H naught when lambda is not in the discrete spectrum. Well, this is technical, but you can see that you have physics here, because, well, the spectral flow is you fix your energies if you want, your lambda, and you see how the difference between your original object and your fluctuated object evolve for the eigenvalue when they cross precisely this value. So this is a different regularization than the trace of this difference of projections, because this regularization is obtained when you replace this difference by f of h minus f of h naught. You see? When f is a smooth approximation of this. In general, physicists like this. Yeah, but you know, I claim that there are physics when you choose f and not this, because you miss all of this and you have a lot of physics. And the physics is precisely the difference between the spectral action and its asymptotics. Okay? So what I claim is that these are different because, of course, if you work with index, if it's integer valued, so while our function is not necessarily integer valued, okay? So you gain something. So it's time for the precise definition of psi. So first you assume that the difference of h and h naught is trace class. You take the resolvent and you define the difference between the resolvent. You add 1. So since it's a trace class, you define the determinant of 1 plus trace class operator, and this makes sense. This is just the infinite product of all the eigenvalues. So you get something which is an homomorphic function, and then you define psi of lambda by you add a little imaginary fluctuation, and you determine the argument when epsilon goes to 0. This can be done, and then you prove that this function precisely controls the trace of this trace class operator, and this L1 norm is also controlled by this L1 norm. And this trace formula holds for a large set of functions, at least here, for smooth functions with compact support. So the idea what we have used is that we use h naught is our original Dirac operator, h is the square of the fluctuated Dirac operator, and when you compute the difference between the power to half the dimension of the resolvent of these two operators, then you prove that it's a trace class operator. So if you define C as a set of functions which are, say, sympathetic enough, okay, and here you have an example, so not so complicated, then for this class, this difference is trace class, so the trace formula holds through. Okay? So this means that, again, if we have this, and if we have a control on how the component of the connection mu is given by this simple control, we have no deep control on the derivative of mu, just constant, okay, then our previous conditions are satisfied and the trace formula holds through, which means that the variation of the spectral action is well defined. So we have a huge set of functions which are under control and for any scale of energy. And the proof uses something which is the pseudo-differential operator on RD. I don't know if you want to see this. Well, you are silent, so maybe not. That's important, guys, you know. Anyway, so what's the conclusions? Conclusion is that variation of spectral action for a commutative spectral triple perturbed by a gauge potential will be given by a simple formula by a simple formula for this action and its universal asymptotics, but it's true even when f is non-positive and even for a step function. So if you lack step function, you can jump until this conclusion, and this is valid for this function even if this has been done in a compact situation, well, by Estrada, Garcia Bondia, and Varelli many years ago. As I said, but it was true, it was satisfied in the C0 sense. And when you put your nose in what means C0 sense, well, you will see that it's almost bullshit, it's almost terrible. So, okay, of course, here you have technical assumptions, so you can make some extension in different situations, and you can control higher orders of the field strength. So there exist formulas for f cubed, and for f4 you need a good student, and so on and so forth. It's like computing, quantum loop Feynman diagrams. So okay, I guess I will stop here.
Thank you very much.